node, it will take more time. If you search an element that is not there in the tree, that will be even more time. So yeah, we will find a way to search to find out the optimal solution for the given tree. First, let's say about binary search tree. What is a binary search tree? In a binary search tree, there will be a root, and all the uh, elements that are present on the left side of the root will be less than the root, and all the elements which are present on the right side of the root will be greater than root. Right. Right. So while searching for an element, we'll start from the root and we'll compare it with it. It's like the binary search. If we see whether, let's take an example. I'll take 5, 4, 3, 7. If I search for an element 10, first I will compare it with 5. It is greater than 5. So I'll go to the right side of 5. 6. 6 is less than 10. So 10 will be on the right side. 7. 7, we don't have, it's a leaf node. We don't have anything. So element 10 is not present in the given list. So what we are doing here basically, we are comparing. Whenever we search for an element in the tree, we're comparing it with the root and we're deciding whether we have to go to the right side of the subtree or left side of the subtree. And we're continuing this process till we find the element or till we get an leaf node. What will be the optimal solution? An optimal solution will be the solution in which we'll take less comparisons. Right. Less comparisons. So creating an optimal binary search tree involves arranging the nodes in such a way that the cost of such operations is minimized. So how can we minimize the cost of operations? Generally, if you take equal weightage to all the elements, that means you search each element equally. We don't know the frequency of searching. If the frequency of searching the element 7 is 10, and if I search all the other, if I don't search all the other elements, then this tree, this is also a BHT, right? With the same elements. But every time I'm searching for the element 7 only, then this will be optimal because with one comparison, I can directly say whether I can directly successfully find the element that I'm searching for. But in this case, I have to compare it with 5. I have to compare it with 6. I have to compare it with 7. And then I'll get to know that 7 is present in the tree. But here, if I consider this tree, where I search for 7 only every time, with one comparison, I get the solution. So if I know the frequency, then I can say this is optimal for that question. But what if I search for 6 every time? Then 6 becomes root. But what if I search 6 7 times, 5 4 times, 4 3 times, 3 2 times, and 1 1 time? Then I need to know a solution or a way, an algorithm that in which I can find the optimal solution. This is our main motto for this setup. So generally, when we need an optimal, remember this point, when we need an optimal solution, we use dynamic programming. And when we need all the solutions that are possible, uh, then we use backtracking. So when we use backtracking, we'll get all the solutions. And when we use dynamic programming, we generally get the optimal solution. Optimal here means the less number of comparisons for this optimal binary search. Let's take an example. Let the keys be 10, 20, 30, 40, 50, 60, and 70. Now, if I now let the frequency be 1 for every, then we know that I'll draw a balanced binary search tree. Balanced binary search tree will be optimal if you don't know the frequencies. If you consider that all the frequencies are same. Now the search complexity for this will be log n, because every time I'm removing half the elements, right? If it is greater than 40, I'll go to the right side. I'm ignoring all the elements that are present on the left side. And in a balanced binary search tree, the elements that are present on the left subtree and right subtree will almost be equal. And my search may be successful or unsuccessful. You have to keep this. The element that I'm searching in the tree may be present in the tree or may not be present in the tree. This is the optimal solution if you don't know the frequencies or the frequencies are equal. Now, consider an example. I'll just take 3 elements, 10, 20, and 30. What are the possible trees, binary search trees for 10, 20, and 30? 10 can be the key, 20 can be its right subtree, 30 can be its right subtree. This is one formation of a tree. 10 and 30 can be its right subtree and 20 can be its left subtree. This is one formation. Now I have the 20 as my tree, then 10 and 30. And there is no other way if 20 is the root. Right? Now I'll take 30 as my. This is one formation. Now my number of keys are 3. And how many trees I found? 5. If you want the example for it, if there are n keys, the number of binary searches that can be formed are 2n cn by n plus. Keep this in mind. We'll use it in the form. Because for 3 keys, you can do this. For 4 keys, you will do this. But what if we have more than 4 keys? You cannot draw all the trees, right? There should be some easy. So for 3 keys, we have 5 binary searches. Now let's see. Let's calculate the comparisons. I'm considering as there is no frequency. All the frequency of searching each node is equal. I'm taking that concept. So for 10, it will be 1 comparison. And if it is greater than it, let's consider the successful searches or the possible searches. It will go on the right side. So 2 and it will be the third comparison. So first comparison it will do with the root 10. Second comparison it will do with 20. Third comparison with 30. Here also it's the same. Right. But here it will do one comparison with 20. If it is less, it will do the second comparison with 10. And if it is greater, it will do the second comparison with 30. Do not compare with 10, and again it doesn't come with 30, right? The first comparison will be with 20. The second comparison will be either for 10 or 30. It will not be both. Here it will be 1, 2, 3. Here it will be 1, 2, 3. Let's calculate the average comparisons. The average comparison for this tree will be 1 plus 2 plus 3 by total 3 nodes, which is 6 by 3 is 2. Even for this, it will be 2. Even for this, it will be 2. And for this, it will be 1 plus 2 plus 2 by 3, which is 5 by 3, which is a bit less than 2. So the average comparisons in the balanced tree when the frequencies are equal is the balanced binary search tree, where the comparisons is less than the average of all other cases. Here also it will be 1 plus 2 plus 3 by 3, which is 2. Here also it will be 2. So because this is a balanced binary search tree and the frequencies are equal, frequencies of searching are equal, this is my optimal solution. Now, that is the case when we don't have frequencies. But given in searching the optimal binary search tree, will be given the frequencies of each node in the tree. So now let's say I also have frequencies of search. Now I should find which tree is optimal. Let's see for 3 keys first, because then you'll understand easily. I'll take the same keys 10, 20, and 30. And the frequencies I'll take as the frequency of searching 10 is 3, the frequency of 20 is 2, and the frequency of searching 30 is 5. Okay. Now, let me draw all the possibilities that we have. The possibilities are these only, right? Let me draw them. 10, 20, 30, and 30, 20. 20, 10, 30, 30, 10, 20, 30, 20, 10. The number of comparisons will be the same, right? Only in this case, it will be 1 to 2. In all other cases, it will be 1 to 3. The number of comparisons. But now I also have frequencies. So what will be the calculation? One search of 10, that means 1 into 3 plus 2 into 2 plus 5 into 3. What are the comparisons that I am getting? 3 plus 4 plus 15, which is 22. So with these frequencies, the number of comparisons that I need in this tree is 22. What will be here? For 10, it is one search. So 1 into 3. For 30, it is 2 searches. That means 2 into 5. And for 20, it is 3 into 2. That is 3 plus 10 plus 6, which is 19. What is the number of comparisons here? It is 1 into 3. Sorry. The 20 is the root here. It will take one search, one comparison. Sorry. So for 20, it is 2. 1 into 2 plus for 10, it is 3. 2 into 3. And for 30, it is 2. 2 into 5. It is 2, 6, and 10. It is 18. Here, 30 is the root. 30 into 5. Sorry, 1 into 5. 1 comparison into 5 times I'm searching. So it will be 5 comparisons plus 2 comparisons, and I'm searching it 2 times. So 2 into 2 comparisons, 3 comparisons, and I'm searching it. Sorry, this is 10. So 2 into 3, and this is 3 comparisons, and I'm searching it 2 times. So 3 into 2. It is 5, 6, 6, It is 17 comparisons. Here 30. 1 into 5 plus 2 into 2 plus 3 into 3, which is 5 plus 4 plus 9 is 8. So which tree takes the less comparisons? 17 is less, right? So this is the optimal binary search tree for this frequency and this keys. If the keys are 10, 20, 30 and their frequencies are 3 to 5 respectively, then the tree where the root is 30 and its left subtree is 10 and its right subtree is 20, this will be the optimal binary search tree with the least number of comparisons, that is 17. Now, every time we cannot draw this piece, right? Let's take an example of 4 keys and see the solution, how we can find out the uh, the least number of comparisons and the correct optimal solution of subtree. Let the keys be 10, 20, 30, and 40. So 1, 2, 3, and 4 keys. And the frequencies be 4, 2, 6, 3. And I need a, we need a matrix here. If I have n keys, the matrix will be of size n plus 1 into n plus 1. Let this be I and this be j. My columns are j, my rows are I. This is our cost matrix. So our solution will be, we have to fill this matrix, and after filling this matrix, we'll get to know the least number of comparisons, and it will be at the position 0, 4. That will be our optimal solution. We'll find our optimal solution, and it will be, and we'll also know the number of comparisons. Now let's calculate. We're going to fill this matrix in such a way that first we are going to fill this diagonal where I is equal to j, or j minus I equal to 0. That means 0 minus 0, 1 minus 1, 2 minus 2, 3 minus 3, and 4 minus 4. All this will be 0. So that means I'm going to fill this. And after that, I'll fill all the diagonal elements in this way. That is j minus I will be 1. That is 1 minus 0, 2 minus 1, 3 minus 2, and 4 minus 3. And if you see in the matrix, there will be C of 0, 1, C of 1, 2, C of 2, 3, and C of 3, 4. The weight of something 0 to 4 will be adding every weight or the frequency here. Frequency of this is the weight from 0 to 4. This one, and we'll have one more formula. We'll first we'll try to calculate them like this. C of 0 to 1 the means cost of traveling from 0 to 1, which is cost of traveling from one element to the second element. So cost of traveling from 0 to 10 or 10 to 10 is 4, or and after that it will be 2, it will be 6, and it will be 3. So this will be 6, sorry, 4, 2, 6, and 3, because it is directly, we have only one element in each tree, so we are calculating it that way. And whenever the I and j are same, then the frequency, the cost will be 0. So first I'll fill it. Whenever I and j are same, the cost will be 0. And whenever I have two elements, when I am traveling from 0 to first element, it will be 4, or first to second, it will be 2. It's the same, it's the given frequencies will be the cost. But now I'm going to find C of 1 to 3. We'll ignore this first element and we'll take two nodes every time, 2 and 3, because here we'll take 0 nodes, here we'll take 2 nodes, here we'll take 3 nodes, here we'll take 4 nodes, and finally we'll get the optimal solution. So the possible ways for second and third will be 20 and 30, 20, 30, and 30. 20. So what is the frequency of 20 of search 22? What is the frequency of searching 30? It is 6. And the number of comparisons for this tree will be 1 comparison for the 20, 2 comparisons for 30. And here 1 comparison for 30, 2 comparisons for 20. And the frequency is 2, the frequency is 6. So it will be 1 into 6 plus 2 into 2, which is 10. 2 into 1 plus 6 into 2, which is 14. And because which one is less than this both? We want the optimal solution. So we want the least number of comparisons that will take. That is this 10 is least. And what is the root for the optimal solution? The third node, 30. Third node is the root. So I'm going to fill it. C1, 3. Here 10 is my least number of comparisons, where root is 3. All right. In the same way, I'll calculate for 2, 4. We'll ignore 2. I'll have 3 and 4. 3 and 4, 30 and 40. 30 and 40. This is one tree that can be found. This is one other tree that can be found. The number of comparisons will be 1, 2, and 1, 2. But for the frequency of 36, the frequency of 40 is 3. 40 is 3, 30 is 6. 6 into 1, 6 plus 2 into 3, 6 is 12. 3 into 1, 3 plus 6 into 2 is 12. 15. Which one is less? 12 is less. And what is the root? No, 30 is the root. That means C2, 4. Here, 12, and my root is 3. Right. Now let's calculate here. We didn't calculate 0, 2, right? C of 0, 2. We'll ignore 0, 1, 2. That means 10, 20. We have 2, 1, 2, 1, 2. And what are the frequencies? For 10 it is 4. For 20 it is 2. For 10 it is 4. For 20 it is 2. 1 into 2 plus 4 into 2 is 10. 1 into 4 plus this is 8. Okay. So 8, and what is the node? 1 is the node. 1 is the root. And 8 is less than 10. Now we'll calculate this diagonal where j minus I is 3. That means 3 minus 0, and 4 minus 1. That is C of 0 comma 3, C of 1 comma 4. Now we will take 3 nodes. For this diagonal, we will take 3 nodes. For this diagonal, we took 2 nodes. For this diagonal, we took 1 node. For this diagonal, we took 0 nodes. So now we'll take 3 nodes, ignoring the first. So for C 0 comma 3, what is the weight? The possibilities are taking the elements are 10, 20, and 30. We'll get 5 possible trees, right? I'll draw them 10, 20, 30, and 10, 20, 30. Sorry, this is 10, 30, 20. This is possible. Where 10 is the root? If 20 is the root, we have only one tree. And if it is 30, if 30 is the root, we'll have two trees. Okay. Now, we'll calculate the cost matrix, and now we are calculating C 0 comma 3. But every time we cannot draw the matrices, the trees, and write the comparisons, their frequencies, and yeah, we cannot calculate, right? And after finding all this, we have to see the minimum of all these, and we have to select that as the optimal. But instead of this, we'll derive a formula where C 0 comma 3 will be minimum of C 0 comma 0, C 0 comma 1, C 0 comma 2 plus C 1 comma 3, because 0 is already 1, C 2 comma 3, C 3 comma 3 plus weight of 0 comma 3, where weight of 0 comma 3 will be sum of all frequencies till that node. So for 0 comma 3 it will be 4 plus 2 plus 6, which is 12. And if you see the matrix, we already know 0 comma 0, we know 0 comma 1, we know 0 comma 2, and we know 1 comma 3, we know 2 comma 3, we know 3 comma 3, and we also know the weight. Now let's simply select the minimum of them. So what will be the minimum? C 0 comma 0 is 0, C 0 comma 1 is 4, 0 comma 2 is 8, plus 1 comma 3 is 10, 2 comma 3 is 6, 3 comma 3 is 3. And the weight is same for all. So what are these? 22, 22, 22. Right. Choose for 0 comma 3. So we have two solutions here. We can either select this or this because both are same. Both the trees stay same number of comparisons. Okay, give me 1 second. What is the frequency? The frequency is 12. The frequency is 12 and it's 0, 2, PVC of 0, 0, 1, 2, 0, 1, 2, 3, it's 12. That is fine. But C of 0, 0 is 0, 0, 1 is 4. 5, 2, 8, 1. It should be 1 comma 2, right? So, 11, 22, 40, 10. Okay, it is 22. So, and the root may be 2 or 1. See it, right? Okay. So it is 22 and the root may be the first node or the second, because both the comparisons are same. It will be 22 and it is 2. Let's take it as 2. Now we have to calculate 1 comma 4. What will be C1 comma 4? C1 comma 4 will be minimum of C11. C1 comma 1. That is C1 plus C1 right. C1 comma 4 will be minimum of C11 plus C224 plus V8 from 1 to 12. Then C1 to 2 plus C3 to 4 plus V8 1 to 4. to 1 to 3 and 4 to 4. Let's wait from 1 to 4. It will be 1 to 1 is 0 plus 2 to 4 is 12. And for 1 to 4 it is what are the frequencies? And 11. So it's going to be what 23. 3 1 to 2 is 2. 3 to 4 is 3. Is 16. And C 1 comma 3 is 10. That's 4 times is 0. So 16 is less. What is the root is? The third node is 3. And the root is 3. Now let's calculate 3 0 comma 4. It will be minimum of 3 0 0 3 0 1 0 2 3 0 3 plus C 1 comma 4 3 comma 4 3 comma 4 3 comma 4 plus weight from 0 to 4. What will be the weight from 0 to 4? Will be 4 plus 2 plus 6 plus 3. That is 15. It's 15. And if we calculate, we get we know all the other values, right? C 0 0 is here, 0 1 is here, 0 2 0 3. And if you say if we get minimum here, the root is 10, minimum here the root is 20, minimum here the root is 30, minimum here the root is 40. So if we calculate by doing all these functions, we get 26 of the most. And root number 3 no. So this is the minimum for the with least number of comparisons that we need. And every time if we check, you can see the optimal root. So 3 will be the root. 30 will be the root node. 40. And in the second, on the left side it will be 20. On its left it will be 10. This is the optimal solution. With this matrix, we can say this is the optimal solution, and the least number of comparisons are 26. With this, let's form. Now, let me join through my laptop, and we'll see how can we convert this into a matrix. But before that, we will generalize the formula. It will be minimum of C I to P minus 1 plus C A to J plus weight of I to J, where K lies between I and J. It will increment. It will start from I plus 1 to J. This is a formula. With this formula, we will try to write an algorithm, and we will try to fill the cost matrix. And in the cost matrix, the 0th row, the last column, we will get the number of least comparisons. I will simply try to use this algorithm. I'll join through my laptop. Okay, let me share my screen. So we have to use the dynamic program, right? What will be the inputs? The inputs will be the keys and the frequencies, and we'll use a 2D cost matrix that we have seen just now. And with that, we'll try to fill it. Let me start. And what will be the output? The output will be the least. What is the least number of comparisons? Okay. Let's write a program. Optimal BST, which will take keys, comma, frequency, and I need n. N is the length of keys. N is the length of keys, and first I'll fill all the cost. I'll need a cost matrix, right? It is a 2D matrix, and I'll fill 0 for everything. For this 0, for x in range of m, and for y in range of n. Now I have a 2D matrix with all zeros. And what will be the uh, first case is where I and j are equal. The frequency is just the same, right? So for I in range n, the cost matrix I comma I will be frequency of I. Please don't get confused. There my matrix was starting from 0. Here I directly took it from 0 to n. So that's why there will be no 0 0 column, that diagonal. We are ignoring it. For, for what should I for ln range, to start from 2 to n plus 1, where n plus 1 is, that is the chain length, and for I in range n minus l minus 1. Here now I need the column number, right? I have the row number will be I, but the column number will be different. It should change. The column number will be I plus L minus 1 and cost of I j. Now first I'll keep all them as infinity, and if I find less than every time I'm keeping them infinity because if I want to find the least number of comparisons, I need to compare it with something, right? If it is infinity, first I'll find some number of comparisons which will be less than infinity. So I'll update it, and after that, if I find number or least number of comparisons uh, that is already present in the cost matrix, then I'll update it. If I don't find it, I'll not update it. I'll just keep it the same way. Now I'll write now all the elements will be infinity in the cost matrix. The upper subtree, the right upper tree of the matrix will be infinity. And now if I find a cost which is less than infinity, I'll update it. And even if I find something which is already present and I got a new number of less comparisons, I'll update it. In that way, I'll get the least comparisons, right? It should be from I to j plus 1. So I'll take a variable c where this will be 0 if r equal to I. R is equal to I, or else it can be cost of I r minus 1 plus 0 if r equal to j, or else cost matrix r plus 1 comma j. Can be this also, or can also be the sum of all the below frequencies. It will be the least of these plus sum of, this is the weight formula, frequencies of I to j, j plus 1. Now if the new c is less than that is already present, I'm going to update it. Initially those will be infinity, but afterwards we'll get some cost. But if I find something which I find a new cost which is less than it, I'm updating it. And after updating, where will be my final route will be? I'm going to return the cost matrix 0 comma n minus 1, where I will get the cost matrix 0 comma n minus 1 will give me the least number of comparisons. Let's check it. Let my keys be. We'll take the same solution because we already solved it. We know that, right? 40 and their frequencies be 4263. Right. Now I'm calculating. Then we should get 26. What's the error? 17. Line number 17 is frequency. It is saying as 0, right? 0.0 is, it is 4. Find range of n. Plus 1 and the cost will be, I think we did a mistake here only. Let's see. It is 0 if r equals to I, else cost of I comma r plus 1 plus 0 if r equal to j, else cost of r plus 1 comma j plus sum of frequencies of I to j plus 1. Cost of I'm updating it, right? Keys are 10, 20, 30, 40. Frequencies are 4 to 6, 3. See that? What happened here? Let's first see the cost matrix, maybe. Is it the same thing that we got? 4, 4, 8. It didn't calculate for 3 and 4, right? So I think we made a mistake in some for loop. We didn't take his. It's 4. Let me do one thing. And we end. Okay. It is filling the right subtree correctly, but there is some mistake. It's not. It is calculating 0, 1, 1, 2, 2, 3, and 3, 4. But it's not calculating the rest of them. That means, see here. Okay, 0. Okay, we are keeping them as 0, and it's not finding anything which is less than 0. Yeah, I'm not understanding where we did a mistake, but there is a mistake in the for loop. I can know that. I'm understanding that. So, for L in range 2 to n plus 1. Yeah, here. This we have to increase, right? Yeah. Now we'll get 0 to n minus. Now we got 26 as the least number of comparisons. It is a bit confusing, but we didn't do anything new here. We simply followed the formula that I have derived in the end and added some logic to it. I kept all of them infinity before, and after that I am just updating them if I find a least number of comparisons which is already present. So I'm basically filling the cost matrix, and after finding the cost matrix in the zeroth row, my last column I'll have the least number of comparisons, and from the cost matrix we can also say the optimal rate. I'll share you this file and please take some. Please take a break for 5 to 10 minutes, and we'll start the second session also, the seventh question. For the seventh question also, we'll first derive it with pen and paper. We'll get a formula. We'll try to see it, and we'll simply turn that formula into a algorithm. We'll start it in 10:35. Now I'll share this file. Okay. Now let's start from lab 7. Is developing a program to maintain the running time for traveling salesperson. You can see traveling salesperson. Let's try to understand the question first. A traveling salesperson is nothing but consider that you are a postman. You have to give letters to everybody and you have to come back to your home. You start from your home and you have letters addressed to three more locations A, B, C. You can go to A from home and come back. You can go to B from home and come back. You can go to C from home and come back. And you can go from any place to any place, right? This will be the right. These are the possibilities. But you have to find the solution for a traveling salesperson using dynamic programming. So again, you'll get optimal solution. What will be the optimal? From home, we'll start. We'll go to all other places only once. We'll not go to the same place twice, right? It is a time waste. We need to go to sorry for the delay. So we'll get the optimal solution. What will be the optimal solution? Optimal solution will be the postman or the salesperson will start from home. He will go to all the other set of nodes that he have to travel only once. only once, all vertices, and he'll come back to home. And he'll do all this in least time. He'll try to finish his job in the fastest time that is possible. That will be the optimal solution. One such way to find this is brute force, where we'll write all the possible ways, A to B to C, and again to home. We'll have the first node and the last node will be the same. We'll have combinations of rest of B, A, C, C, A, B, C, B, A, and so on. And we'll calculate the from home to A, we'll have some X time, A to B, Y time, Z. We'll add that, we'll get some time taken, we'll find the least one, and we'll say that is the optimal solution. This is beautiful. We'll see all the possible ways and select the least weighted. And the second one is dynamic programming. We'll use dynamic programming and we'll find the least number of ways that we can form. Let's take an example. I'll take 4 nodes, A, B, C, D, and the traveling person will be starting from A. I'll be having all the ways from A to A, A to C. I have all the ways, right? I can go to B from A, D, C. I can go to B from A, C, D. I can go to C from A, B, D. I can go to D from A, C, B. Let me take an adjacency matrix. So we'll be given the adjacency matrix, which is nothing but the weights from A, B, C, D to A, B, C. A, B, C, to D to A, B, C, D. I'll take a random. From A to A, B to C will be 0. And afterwards, from A to B it is 16, but from B to A it is 8. So don't take it logically that if the traveling time from A to B is 16, it should be 16 for the B to A also, right? But this is a B, and this is not only for the salesperson, but it is used in several contexts. So if it is really used in postman or salesperson, it will be the mirror image. It will be 16. But let's do it for an if we calculated something for this matrix, it is useful for the same matrix that I have discussed. So I take something in a random numbers. So this will indicate that the time taken from for the salesperson to go from A to A is 0, A to B is 16, A to C is 11, A to D is 6. In the same way, B to A is 8, B to B is 0, B to C is 13, B to D is 16, C to A is 4, C to B is 7, C to C is 0, C to D is 9, D to A is 5, D to B is 12, D to C is 2, and D to D is 0. And I'm starting from A. So we'll be given an adjacency matrix and it will give the source also from where we are starting. From A, now I'm using dynamic programming and writing it here itself. What are the possible ways? I can go to B. I can go to C. I can go to D. If I go to B, after B I can go to C or I can go to D. Right? And after C, I can go to B or D. After D, I can go to C, B, or C. After C, I must go to D. Right? Did you understand? I'm starting from A. After A, I can go to B or C or D. B or C or D. If I took the path going from B, I can go to C or D. Because no node should be occurred twice, right? So if I choose C, after C, I can go to only D. But if I go to D here, I can go to C. If I go to B, I can go to D. If I went to D, I'll go to D. If I went to D here, I'll go to C here. If I went to C here, I'll go to B here. These are the possible ways. A, B, C, D, A, B, D, C, A, C, B, D, A, C, D, B, A, D, B, C, A, D, C, B. And finally, I'll go to A, right? In all cases, I'll go to A. In the end, I should go to the home. That will be A. Now, in dynamic programming, we will backtrack. We'll come from the leaf node. This is not a tree, but we will come from A. What is the time from D to A? D to A is 5. Okay. Now D to A is 5. And what is the time from C to D? C to D is 9. 9. But in this route, if you go, it will be 9 plus 5, right? 9 plus 5, which is 14. And B to C, it will be B to C, it will be 13. 13 plus 14 is 27. Here we got 27. If we choose this path, the time taken is 27. What is if we choose this path from C to A? It is 4. From D to C, it is 2. D to C, it is 2. And C to A, it is 4. So it will be 6. What is B to D? B to D is 16. 16 plus 6 is 22. We got 22 if we choose this path. Now we have to select the optimal solution. So which one is less? 27 or 22? 22 is less. So I'm selecting 22. And what is the 22's path? A, B, D, C, A. This is the 22's path. The similar way, let's calculate for all the possible ways. D to A, it is 5. B to D, it is 16. 16 plus 5 is 21. C to B is 7. That is 28 in this way. B to A is 8. D to B is 12. 12 plus 8 is 20. C to D is 9. This is 29. So the optimal is 28, which is less. That is this way. Now let's calculate here. C to A is 4. B to C is 13 plus 13. 13 plus 4 is 17. D to B is 12. 12 plus 17 is 29 in this way. D to A is 8. C to B is 7. 7 plus 8 is 15. D to C is 2. That is 17. Right? 17 is the list. We selected 7. And out of 22, 28, and 17, 17 is the list. So we are selecting 7. So the optimal solution here is the path that is A, D, C, B, A. A, D, C, B, A. And the time taken is 17. The least weight is 7. Right? Now, let's derive a formula for this. If I take I as the starting vertex, and S is set of vertices that salesperson should visit exactly once and gets back to starting point. Then our formula will be minimum of weight from I to J plus a recursion. I call the same function J to set of S minus I. Where J is a subset of S. And the recursion will end to the end case, right? Where it will be X comma an empty set. Then it is the same rate from X to I. I is the starting index. I is the starting vertex. This is a problem that we are going to solve. Now, for the example that we have solved here using pen and paper, we'll see how it is working in this form. Now, my I is A, and what will be my S? If I is A, the S will be set of B, C, D, right? Okay. Now, I'm going to calculate this. G of I is A, S is equals to minimum of the value of A comma B plus V of B is G of J. First I'm selecting B as J. And what will be my S? My S is B, C, D, and J is B. S minus J. So from BCD, I'm removing B because I already selected it. My new set will be C comma D. I have to calculate this. And what if I selected A to C here? J is C. I'm going to C. And G will be C to either B or D. It is minimum of this one or A to D plus G of D and D to C. Right? We have to calculate this. First, let's calculate this because if we want to find this, we only want this. What will be the G of B comma set of C and D? That will be minimum of B to C or B to D or B to D plus B of C and set will be D, right? B of D and set will be C. Now I want G of C comma set of D to calculate this. That will be C to D. I have only one option. C to D plus G of D2. What is this? Set minus J. My set is contain only D. If I remove it, it will be J. It will be an empty set. So what are we saying that D to X2 an empty set? It is the weight from X to the starting vertex. That means D to starting. That means D to my starting vertex is A. That is 5. So this is 5. This is 5. And what is C to D? C to D is 9. So this is 14. In the similar way, I also want for D to C. This will be D to C, D to C. That is, what is D to C? D to C is 2. C to A is 4. That is 6. Alright? That means this is 14. This is 6. What is B to C? B to C is 13. B to D is 16. 16 plus 6 is 22. 13 plus 14 is 27. I'm selecting 22 because that is the minimum. So G of B set C and D is 22. This is 22. Right? And what is A to B? A to B is 16. So this is 38. The similar way, we have to calculate these two ones. Now, what should I calculate? G, C, comma, B and D. I have to calculate this. And I could also calculate G, B comma set of B and C. Right. This will be minimum of weight from C to B, weight from C to D plus G of B to set of D. This will be G of B to set of D. What will be G of B to set of D? This will be G of weight of B to D plus G of D to set minimum of and what will be G of B to B? This will be weight of B to G plus G of B to NPC. What is B to A is A, B to B is 12, this is 20, this is 20, C to D is 9, this is 29, and G of D to B to D is 16, 16 plus 5 is 51, this is 21, C to B is 7, so this is 28, 28 is less than 10, so I'm selecting 20. G of C to C set of B and D is 28. And A to C is 11. So this is 39. Right? So I'll calculate G of D set of B and C. That is this. This will be minimum of weight of D to B or weight of D to C plus G of B to set of C. G of C to set of B. And then B from set of C. This will be weight of B to C plus G of C to C. Energy of C from set of B will be weight of C to B plus G of B to C. What is P of C to B to 5? It's 8. C to B is 7. This is 15. C to 5 is 4. B to C is 13. This is 17. This is 17. This is 15. D to D is 12. 12 plus 17 is 29. D to C is 2. This is 17. 17 is minimum. So D of D is 17. A to D is 6. That is 23. Out of all this, 23 is minimum. So I got this. A to D is yeah. A to D is 23, and that is the minimum. So 23 is the least weight. And what is the actual least? Because that is the least. What is the path A to D first? A to B. And G of E to B comma VC, that is here. Which one did I choose? I choose this one. That is D to C. So D to C and D to C. After C, I went from C to B. So that is C to B. After B, I again went to A. So the optimal solution is ADCBA. And I'm going to the least time taken is 23. Right? Here also A to D is 6, 7 plus 6, 23. So after my final solution is here will take 17, but I will 23 for the whole solution for coming back also. Till here it is equals 17, and from A to B it is 6. Right. Simply use this formula. Now let's try. Now let's try to actually this is the logic behind the trunk salesperson using dynamic programming. But you can implement this logic using several things, right? You can use iterations, you can use bit operations, and because here we every time we are using recursion, let's try to use recursion, but we have to be very careful. Even one small mistake, it will be for a infinite loop, or you should be very careful because only for 4 nodes, we took only 4 nodes, right? A, B, C, D. Only for 4 nodes, we need to calculate all this using recursion. So think if there are more nodes, like 7, 8, 9, 10, it will be very lengthy. So we'll try to write a program. I'll join through my laptop and we'll try to implement this formula in Python. Sorry, every time you have to wait whenever I shift from notebook to laptop and laptop to phone. But I feel it is an effective way if you understand the logic, and after that, if you code, you'll remember it. Now, I need you also to see every line with me because this will be a bit lengthy to implement. But I'm going to use the same logic that we have discussed. We're going to use the same thing using recursion. But uh, if you find any mistake, you can correct me in between also. Because even if I do a single mistake, we are taking so much time to debug it, right? I'll use NumPy and I'll also use iter tools. If you know iter tools, the library iter tools, that is very useful. I need the combinations, right? What did I do when I used pen and paper? I I wrote all possible ways basically. So here iter-tools will be helpful for me to get the all the paths. And let's also see the time taken. And just import time also. And I'll write a program, traveling salesperson, it is TSP, which will take a matrix, distance matrix. Distance from all the nodes to all the other nodes. What I need L is my length of matrix. I need something, a dictionary or a set, where I'll store the cost of reaching each city because I need it from a subset. This will be my subset. What is the base case that we followed? I'll fill all the cost from starting from the city to every other node. So that will be for k in range. Let it start from 1 because I don't need the initial one, but I need all other nodes. K to n. My cost, let this be capital because then it will be. This is basically my cache because I'm removing and adding all the other nodes, right? I need a logic in such a way that I'm left shifting k and k. That means I'm selecting a node from k to k and I'll give it a distance. I have distance matrix, right? From distance matrix, it will be 0, comma k for 0. What is this line doing is it is storing cost and indicating the starting city as 0. I'm taking the starting city as 0 and indicating it at the cost from 0 to 1, 0 to 2, 0 to 3. It is basically doing that. Now I should write a recursive step to compute cost for the subsets of the cities. What is the subset of the cities? If I'm starting from A, my subset is B, C, D. If I select B, my subset is becoming C and D. And if I'm selecting D, my subset is D. If I have only one element in the subset, I'm selecting it and I'm going to the starting index. That's what we did, right? So that I'm going to convert into a code for subset size in range 2 comma n for subset in. Now I need all the combinations. The tools dot combinations which range from 1 to n because I already took 0 and 1 and I filled it, right? Sub till subset size till subset size. I'm generating all the combinations of cities. I'm also going to use bits here because that will be easy. It's very hard to remember and implement, but if we find the correct logic, it will be easy. For each bit in the subset, I'm going to left shift it so that uh, I'm converting the subset into bit representation basically, or equal to 1 left subshift the bit. Now I converted the subset into bit representation, and for each k in subset, I'll have a previous, that is bits, and or bits and or right shift k, removing k as my subset, and I'll store the result here for each m in subset. If m if m is my starting index, or m is k, I'm ignoring it because I shouldn't uh, go to the same vertex two times, right? I'm going to skip it. For skipping, I'm continuing it, or else I'm appending it into the result. First, let's append it into the result, and after that, we'll see whether that is optimal or not. And 0 plus, I should also add the weight, right? Distance matrix of m of k. M. Okay. Now I have appended it. I should also see whether I should also add this one, right? This one will be the minimum of all the result that I have. I'm storing everything in the result, but finally I should select the which one is minimum. Here every time I'm also adding the key because I also need the path, right? Right now I'll add all the paths like this, and in the end we will just reverse it. If we reverse it, we'll get the optimal path for the salesperson. Okay. With this, now we have to connect it with the starting position also, right? We have to go to the final position also. This will be my new bits, and my new result, and for k in range 1 to n, I'll add everything into the result. C of zero plus distance matrix of k, sorry, k of 0 comma k. I'm adding k also. My optimal time taken, comma, my parent will be minimum of my result. The same thing that we did above. Now, what will be my path? My path, I stored it every time in the parent, right? Optimal path and the parent. So I just now need the parents. So it is simple. For I in range 1 to n minus 1 path dot append. I'll append the parent. I'm adding the city to the parent and my new bit. I'm again right shifting because to remove the node. Now I'm updating it. C is its comma parent. My bits will be new bits. This is also in the function, right? Now my bits will be new bits and I'll simply append this path. Then after that, now I think the path will be in reverse, right? Let's check. If it is in reverse, we'll add just. It's very easy to reverse a list, right? Let's see. Let's take the distance matrix. My distance matrix is. We'll take the same uh, question that we have solved in paper using pen and paper. Give me 1 minute. We got 23 as the output, right? Okay. Okay, it is 0, 16, 11, 6, comma 80, 13, 16, 80, 13, 16, comma 4709, 4709, 512 to 0, 512 to 0. Now, my this is parent, my optimal and path will be
equal to TSP of distance matrix. And I'm going to print them optimal and path. Okay. Now I think it will take so much time because I use so many bit operations. I have to see what happened with it. Yeah. It's running. Okay. We got. But there is something different in the path, right? The path we got is different. We got the optimal least complexity correct only 23. And what should we get? ADCB. A is 0, but we got a different one here. We have to reverse it basically, that we will do. But every time we have to 1, right? We have to add 1 and it is also reverse. We have to do something. Let's convert it into list also. My path is different here. I have to reverse it basically. So I will convert into a list of reversed of my path. I missed 3 here. Let me check. Where is my path? A subset of size 0 to 1. I'm getting combinations from 1 to n and subset size. Okay. Here we don't have the error also. Actually, what should it be? It should be 0, 3, 2, 1, and 0. Fine. 0, 3, 2, 1. A 3 is missing here. That means in a loop we ignored 1 and we started from something, right? I'm getting all the combinations here correctly or not. I'm taking it from 1. I should take from 1, right? Because I don't need. For k in set. And my result is an empty list. And if I think in this line I did a mistake because I'm appending something into result. I this comma n plus distance matrix of m to k comma n c of bit Okay. Yeah, I think for k in range 1 to n, result dot append. Yeah, here I have to see C of bits from a k of 0. Path is for I in range. Okay, here it should start with 0. Yeah, I ignored it here. Yeah, now I got the path. 0 is A, 1 is B, 2 is C, 3 is D. So A, D, B, C. We got the correct one. Let's send you this file also. Okay. With this, let's stop our session here today. But if you understand the logic, you can use several different ways to turn that into a code. We'll again meet for the eighth lab, which is n queens. That will be very interesting because we have to keep n queens in an n cross n matrix in such a way that no two queens are attacking each other. We'll have in that we'll have so many different solutions. So there, I think we are using backtracking because we need all the possible solutions. We don't need the optimal solution. There is no optimal solution for it, but we need all the possible solutions. That will be a bit that will be interesting because we are it's like a puzzle to solve, and if we solve it, we'll enjoy it. Okay, thank you. Have a nice day.